friends, welcome back to another video. This is the ultimate grind for BITSAT 2025. We are here with the question bank series. With every episode of this series, we are getting 10 questions stronger in every BITSAT chapter. Okay, so that is the motto of this series. I hope you have been following me for a while now. And today we are discussing the chapter of magnetism and matter. So previously we have discussed all the 11 standard chapters and all the 12 standard chapters that come before this chapter. So if you have not seen those, please do give it a watch. They are quite BITSAT relevant, and we have done some BITSAT relevant concepts and questions in them. So yeah, do check them out. I'll make the playlist available in the description box of this video. As far as BITSAT is concerned, this particular chapter is not very important, so I won't ask you to give it a lot of priority. Today we are going to do a certain few questions. You can focus on those key concepts. So if at all you have a question from this chapter, you can tackle it. Okay, so the previous year trends, if you see, 2 questions straightforward from the concept of magnet. Okay, we'll come to the questions. Then we have earth magnetism, so angle of declination, dip, all those things. So from there, also a hot topic in this chapter. So 2 questions from there, and then questions from hysteresis, and you can have the material, right, paramagnetic, ferromagnetic, diamagnetic, and their properties, and the hysteresis curve for a permanent magnet, electromagnet, and stuff like that. Okay, so please remember those key points in theory. We are going to do some questions. You can extend on that knowledge okay, further, learning similar concepts in this chapter. Okay, so that is the motto of this particular video for this particular chapter. Okay, just extend on what I'm going to do today, and you'll be able to tackle any BITSAT question for the attempt of 2025. Okay, so stick with me. Let's get this done. This will be a short one, and let's begin with the video. So question 1 and 2 over here. I'm answering the same questions 3 times now. Take 3. Okay, so forgive me if there is some pre-marked thing. Okay, so let's begin with question 1. Here we have a magnetic needle which is made to vibrate in the time period t. Okay, it's made to vibrate in the field h. It has time period t. If it's vibrated in the field 4h, what will be its time period? Now t, as you might know, has simple formula 2 pi under root I by mb. Okay, this might not even come in this chapter, right? This might come from SHM. Okay, so t is proportional to, you can see, rest of the things remain constant. Needle is same, moment of inertia is constant. So we have proportionality with square root of b, right? So you can see the field becomes 4 times. So the time period is inversely related. So 4 times square root of that 2. So the field should become inverse, right? Half. Okay, so sorry, the time period should become half. Okay, or you can go by the old school method. So I'll take T2 by T1 ratio. Okay, so it is inversely related. So T1 B1, T2 B2, right? Inversely related to the square root. So B1 is H, B2 is 4H, H cancels, square root of 4 is 2. So half. So T2 will be half of T1. So T1 you can take to the other side. So T1 is original time, right? Time period. So T. So same answer, right? So the same concept that T is inversely proportional to the square root of B. Let's come to this one. Here we are asked for the unit of magnetic strength. So M is equal to IA. This is magnetic dipole. So just like electric dipole, you have charge into distance of separation. So charge is like the electric field strength, right? So here also you'll have magnetic pole strength. So pole strength into distance of separation. Okay, so similarly analogous to electric field, you have the magnetic dipole. Okay, so electric dipole, magnetic dipole, and this is I into A for the time being. So this we are supposed to find its unit. So if you see, this is I, so amperes. Don't confuse it with this A. I'll write amperes, okay, AMP, and this A is meter square, right? Area, and this distance we can divide again in meters. So ampere meter, right? AM, which is option B. Okay, so that's the simple idea behind this question. Okay, you are just supposed to substitute magnetic dipole as a pole strength into distance, and you get your answer. Over to the next set of questions. Let's discuss question 3 and 4. Here in question 3, we are told that the vertical component of Earth's field, so let's call it BV, is equal to the horizontal component at a certain place. So the angle of depth. quite a standard question, right? 45 degrees, because tan of the angle of dip delta is BV by BH, right? If these two are equal, the ratio will be 1. And what angle tan theta is 1? Okay, I didn't frame that correctly. Okay, tan of which angle is 1? Okay, so tan of 45 degrees, right? So at 45 degrees, of course the vertical and the horizontal component will be equal in magnitude. Okay, so that is quite a standard question. So let's come to this. So the major concept of focus was this, so that you know this simple formula. Okay, let's come to question number 4. Here we are placing, firstly we have a uniform magnetic field. So uniform field, parallel lines, right? Just like electric field. So in parallel to the plane of the paper, so like this, from left to right, yes, from left to right, not right to left. Okay, so when a bar of soft core iron, now this is a soft core ion. Ion is like a ferromagnet, right? Soft core ion is a ferromagnet. Okay, so is placed in the field. So what will happen? It will attract, right? Bring the magnetic field line closer to it, right? It will make more lines pass through it. Okay, so that is what a ferromagnetic substance does, right? So if you see this one, the lines are still parallel. There is as such no effect of soft core ion. Okay, so this might not be correct. Let's come to this one. This is making the field go away, right? Kind of go away. Here, whereas if you see the field lines are coming from far apart and they are going into this ion core. Okay, so this is quite showing the typical property of a ferromagnet, right? So whereas this one, it's like the field completely changed its direction because of the placing of soft core ion. This can't happen, at least not for a ferromagnetic substance. Okay, so yeah, so the correct choice here has to be option B. Okay, it's making more field lines, more number of field lines pass through it, right? That's typically a ferromagnet like soft core ion. So that's about these two questions. Over to the next. Question 5 over here, which of the material is used to make a permanent magnet? Okay, so what properties or the hysteresis curve property should a material have so that we make a magnet out of it? So if you see, if we want a magnet, we want high retentivity, right? So if you even when you remove the external field, of course you have to make a magnet by magnetizing it. So when you remove the magnetic field, it shouldn't be the case that a magnet has lost its magnetism. Okay, that's very absurd, right? So the magnet should remain a magnet, so it should have high retentivity, and also if you see coercivity, it also should be high, right? The field that should be applied in now retentivity is this, right? If you know the typical hysteresis curve, okay, so retentivity will be this and coercivity will be this. The field applied in the opposite direction to demagnetize your magnet, okay? So that should also be high, right? So you just can't demagnetize a magnet easily, right? It should remain a magnet. So that is what you can think about. It should remain a magnet, so it should have high retentivity. Even when the field is removed, it should retain its magnetism, right? It is a magnet. It has to be a magnet. Okay, so and also you can think that when you apply any kind of stress or maybe field in opposite direction, it should not demagnetize easily. So it should have higher coercivity. Okay, so both high. And there are different types of material. You might speak of electromagnets and two or three more. Okay, so they'll be mentioned in your NCRT. So you go through them. Okay, which one has which properties. Okay, this is quite intuitive. Also the others, if you look at their properties, you'll be able to relate to it. Just like I told you for the magnet, it should retain magnetic field and it should not be demagnetized easily. Okay, so you can think along those lines for those materials, and there will be a list of 2 or 3 more in your NCRT, and that you can remember. Okay, let's come to question 6. Okay, here we have two magnetic dipoles A and B. This point P is the midpoint. Now remember, for a dipole, the distances are always measured from the center. Okay, so even if this 2D was not mentioned, they have told you the separation between them is 2D, right? So you measure from the center of this dipole to the center of that dipole. Okay, distances for a dipole are measured from the center. Okay, even in the case of electric, right? So their axis is perpendicular to each other. Yeah, as you can see, this is along this length and this is along y-axis. Okay, x-axis, y-axis, you can see. Okay, so now the magnetic field at point P. Now if you see for point A, now let us consider this point P is very much bigger, okay, very much far from the actual dipole distances, okay, so that this d small, this dipole distance will be very less as compared to your distance of point P from that center of the dipole, okay. So that assumption is taken care over here, okay, although you it's not mentioned in the question, you are going to follow that assumption since you won't get otherwise such simple answers, right. So think along the line of the answers. So B1, you can see magnetic field due to A, or we'll write BA, is at a eggshell point, right. Eggshell is twice equatorial, right. Eggshell is twice equatorial, so it will be and along the direction, right. Mu 0 upon, now you'll have 2 kp by r cube, right. In case of electric dipole, so same logic you can use. K over here will be mu 0 upon 4 pi, and this 2 because eggshell is 2 times equatorial. So then magnetic dipole, so m by what is the distance from the center of the dipole to point P is d, okay. This d is very much large, so we can use this approximation. So due to B will be, now this is along the direction of the dipole, okay. So the magnetic moment is like this, the same will follow, okay. Anyways, we are just supposed to see, we'll add it vectorially of course, but you'll see that one magnetic moment is like this, other will be like this, okay. So MA, MB, so yeah, so they'll be making an angle of 90 degrees. So basically we'll be using Pythagoras theorem, okay. So now equatorial, right, for this B, this point P is a equatorial, so the field will be, of course, if the magnetic moment is like this, field will be opposite, right, but doesn't really matter, angle is 90 degrees, we'll treat it vectorially. So what is the equatorial field? This, right, without the 2, so mu 0 upon 4 pi m by dq, okay. So even if you know the electric field formulae for equatorial and axial point, you can reach here, right. K is substituted by this, and P is electric dipole, magnetic dipole, r cube d cube, or r cube, okay, that is just the distance, okay. So yeah, and you know axial is 2 times and equatorial is just single, okay. So same, right, you can quite well derive it another way. So B net will be, so you'll have to add them vectorially, you can see they are making an angle of 90 degree, so B1 square, BA square plus BB square, okay. And now you'll see this is root 4 and root 5, right. Actually one of my professors gave a great intuition for this, like it was one of the SSP class, solid state physics. So there we are supposed to calculate, certain times we calculate the nearest neighbors in the solid structure, okay. In the crystal structure you might have it in a little bit of it in chemistry. So there also we were discussing a planar structure, so you can see the discussion over here is in 2D, right. So intuition sometimes leads us to the wrong answer. So he just asked a question wherein we were doing the simple question, calculation, okay. It was 2 and 1 over here, and just at the first thought we thought it will be root 3, but if you think about it, root 3 comes in 3 dimensions, right. 1 1 1, then you can have root 3, but here it's 4 plus 1, right. There is no way you can have root 3 like with the proper fractions. You can not have like root 3 in the like this in planar structure, right, in that case, okay. So that was just a sidetrack. Anyways, the answer is over here right in front of you. So yeah, even if you calculate, you'll get it, no need of such big intuition from solid state physics, okay. So that's about these 2 questions. Over to the final 2 questions for the day. Question 7 and 8 over here. In question 7 we have a magnet suspended, again same type of question as question 1 that we answered today. So 20 oscillations where angle of dip is this, and 15 oscillations where angle of dip is 60 degrees, the ratio of Earth's total magnetic field, okay. So one key point is it is oscillating in a horizontal plane, okay. So the effect is due to horizontal component of the magnetic field. So time period, as you know, is proportional to square root of B, right. You know the full formula, 2 pi under root I by MB, right, square root of I by MB. So here we are told about oscillations per minute, right. So we can write it in terms of frequency. Frequency is 1 by time period, right, simply equal to 1 by time period. So you can say frequency is directly proportional to this magnetic field, and it is the horizontal component, right? We have the horizontal field. Okay, so we can write nu1 by nu2 is under root. So we are supposed to find the ratio of Earth's total magnetic field. Okay, so at this place and this place, okay, total magnetic field will vary, right? The horizontal and the vertical components vary at different position, and hence the total field also varies, right? So B um, horizontal, right? So it's, you can write it as total cos component of the total, right? The horizontal. So if you have this field, this is the angle of dip. So you'll have BH and BV, right? That is why 10 of your delta is BV by BH, right? Opposite upon hypotenuse. Okay. So the horizontal component. So you can see the relation, right? 10 delta over here. 10 delta is BV by BH. Okay. So the horizontal component. So this is total field, right? Total field. So the horizontal component will be in the cos form, right? So you can write BH as BT cos delta, right? BT1 cos delta and BT2 cos delta, right? This is directly related, and delta 1 delta 2, right? Angle of declination is changing and the field will also be changing, right? So here squaring on both sides, nu1 nu2 square, and we'll have BT1. This is what we are supposed to find by BT2. So the ratio of the magnetic field at the 2 points, and cos of delta 1 cos of delta 2, fine. So nu1 by nu2. So nu1, okay, so 20 oscillations, okay, it's not 20 per minute, right? So get it in the SI unit. So this is 1/3, right? And nu2 will be 15 oscillations per minute. So 15, so you can see the magnetic field will be weaker, okay, since frequency decreased. So here nu2 will be 1/4. Okay, so let's substitute it over here. Nu1 is 1/3 and nu2 is 1/4. So 1/4 that will go on top, right? Or you can take the ratio nu1 by nu2. Okay, nu1 by nu2. So 4, this 4 in the denominator of the denominator will go on top, right? So you can check that. So this is squared, and BT1 BT2, this is what we are supposed to find. I'll write it like this. And cos of delta 1 and cos of delta 2. Cos of delta 1 is 30. Sin 30 is half, cos 30 is root 3 by 2. Okay. Then cos 60 will be half, right? Sin 60 is root 3 by 2. Yes. So this and half will get, the 2 in the denominator basically gets cancelled. So this ratio, what we are supposed to find, will be 16 by 9, and this into root 3. Okay, or no, this root 3 will go in the denominator, right? So 16 is to 9, 9 root 3. Okay, so seems like a difficult answer to get, but it's a simple concept, right? So that's about this question. Let's come to this one, final question for the day. Quite a simple one. You're supposed to find the dependence of susceptibility chi with temperature. Okay, this is the origin. If it's not obvious, this is the temperature axis. Okay, so this is the origin. So that needs to be specified for a specific reason. So since it is a diamagnetic material, it is temperature independent. Okay, for paramagnetic it is dependent, and one of the graphs might show that. You tell me which. So here it is temperature independent. So it can't be this one, can't be this one, right? These two are temperature independent. So same value across all the temperatures, right? And what is the property? What is chi for diamagnetic substance? It is small, of course, and also negative. Okay, small, negative, and yeah, temperature independent. So if you see, this one is negative, right? This is below the origin. So this one is negative. This one is positive. So that can't be the correct choice. Okay, so that's about these two questions, the final two questions for the day. I hope you really enjoyed this short chapter. Okay, and go and revise on the things I've told you across this chapter. Go and watch other videos of all the question banks and get stronger in every chapter. This will help you a lot for BITSAT. Take my word for it, and we'll start with also the question, the mock test series. So if you stay tuned for that, and the grind is going to be amazing, and you can reach amazing results if you keep putting in the work. Okay, so just trust the process. Let's make it happen. I'll see you soon in the next video. All the best, and keep enjoying physics.